Welcome back. I see a few new faces for exam number 3 review, ECE 442-542. I see a few blank faces, but I won't be too offended, although we are talking about the Cupid spec, so my heart might get into this discussion a little bit. But the process for exam 3 should be consistent with what you've been doing all semester. Topic-wise, for exam number 3, we have homeworks 5 and 6, plus what we talked about in today's class. That's okay to be on the exam. It's really, well, it is new. It's rules 4 and 5, but I think that just helps you feel better about these root locus diagrams. It helps you sketch those a little bit more effectively. And we talked about how to find different points, different locations with the gains. That's valid stuff for exam number 3. In terms of pieces or ideas or concepts, there's really sort of 3 main pieces if you group these last 2 together. We sort of put those 2 together with root locus derivation being motivated by P and PI controllers. We sort of derived the root locus rules or strategies or properties using proportional, and then we threw a 0 in there and we fixed a pole at z equal 1 to give us a PI controller. But it was really just adjusting the gain K, again to illustrate root locus. That's the third topic. The first topic is transient performance and z-plane pole locations. Do you know how those are connected? How they are coupled? The second one, topic-wise, is the direct design method of Ragazzini. And the third we just talked about, root locus and PI and P design. All right, for the first topic, let's say this is transient performance and I'll just say z-plane poles. Here I'm going to suggest that we have 3 different sort of categories. One, and this one may be new to you. What if I give you, but it's on some of the practice exams, what if I give you a transient response and I ask you to find z delta, find the closed loop poles for that transient? So this is a system identification problem. Somebody may hit a system with a constant, with a step, and they go, I don't know, here's what I measured. And you go, that's fine, I can give you your model. I can give you your G of Z from this. So this is now going from a transient time domain. This is now the time domain. And you should be able to now find, not Elmo, or Nemo, Finding Nemo. I don't know my movies. Finding Nemo. So now you want to find Z sub delta. This would probably make a good Disney movie. Finding Z sub delta. Might have 2 or 3 engineers that pay to see that. How do we do that? What can you see from this picture that would help you identify? And really, we want not only Z delta, but we might want to find G of Z. I might say, oh, I'm going to tell you that you have a 0 at 1/2 or 1/4, and now I want you to find G of Z and assume it's a second order denominator. Question? So the question was, is it possible to determine the zeros from this? We haven't looked at that particular question, but you might be able to be guided a little bit, but that's not a real easy problem to resolve, to find the zero. So I'm not going to ask you to find the entire g of z necessarily. I might say this plant produced this response. Tell me what some of that g of z consists of. And in particular, I'm wanting you to find the poles, 2 of the poles, and maybe the gain. You would have to identify where this is going. You might say, oh, this is going up to 3 after it settles. And let's say I said this was a unit step response. So you now know what the DC gain is of your system. I put in a 1, and what did I get out? 3. So you now know your DC gain is 3. You also can identify, since you don't know the zero, or you don't know the impact of the zero really messes up your percent overshoot. So you probably don't want to mess with the percent overshoot. But you can find the time to peak, and you can find the settling time. You now have 3 different values. This is, let's say, y of n. Let's assume that this was a discrete system, a discrete time system. You now have identified time to peak, the settling time, and the final value. You now know the DC gain, where I might have told you it was a unit step. The DC gain is now 3. Time to peak, who knows what that is. Let's say that that ends up being 1/4. And settling time, if that's 1/4, what's the settling time? Wow. Maybe 1. And you would have to sort of get somewhat close to these numerical values. But you can physically identify those time intervals. They would have to be labeled on your axis. What I'm suggesting is that this was now 1/4, this is now 1, and those were there on your axis. And you can now say, oh, it was going to settle in 1 second, and it has a peak time of 1/4. What do you know about the peak time? Pi over omega sub d, isn't it? But you also know that theta sub d is omega sub dt. So that omega sub d is actually theta sub d over t. And if we plugged in that, now we know maybe how many, if somebody gives you the sample period, I could either give you that time axis in sample periods or in absolute time. If I've given it to you in absolute time, I might need to give you the sample period, and then you can figure out what is time to peak over t, or you know what t is, and now you can identify what, you know, pi, you can solve for theta sub d. Theta sub d is the angle that these complex poles make with the real line. The settling time is n sub st. And if I've given you the horizontal or the time axis in divisions of capital T, then maybe you can find n sub s instead of an absolute time of 1. But now if I gave you capital T, the sample period, you also know that r n sub s is equal to 0.01. And you can now solve for r. You now have r at an angle theta sub d. You now know the 2 complex poles. Is that clear? So you can experimentally do system identification. If somebody excites your system with a step, you now know how to do that. That's one piece of this first transient performance and Z-plane poles. That's maybe a piece we haven't explicitly talked about, but you have the ability to solve that. System identification. Somebody might say system ID. A second way of looking at this transient performance and Z-plane pole locations is somebody might say, I want a certain percent overshoot, I want a certain peak time, I want a certain settling time. Find a Z sub delta. And now you need to find this intersection of three potentially inconsistent constraints, but hopefully you can find a region in the Z-plane where they are consistent. Meaning, the percent overshoot spec will, let's say, lead to this zeta value. The time to peak spec, and now if you wanted 10% overshoot or less, which side of this heart do you want to be on? Above or inside? Outside or inside? If you want percent overshoot 10% or less. You want your zeta bigger, which is closer to the real line. You want it inside, don't you? I could turn that around. I could say I want a percent overshoot of 20% or more. But you may still need to be stable. So now you're inside the unit circle, but outside the heart of that appropriate zeta value. Is that clear? So I can go either direction on that percent overshoot. If I said something or less, I'm inside the heart. In terms of peak time, that corresponds to a theta sub d, doesn't it? Oops. So this gave rise to a zeta. This is giving rise to a theta sub d. And what if I now want a peak time less than what that angle gives me now, which way do I move that angle? Do I increase that angle if I want a smaller peak time? Flip the coin? It's yes, isn't it? You need a bigger angle for less peak, to get a smaller time to peak. You need to make that system faster. Your angle is bigger. It's getting to where you want to go much quicker. So now and then you might have a settling time spec, which gives you a radius. And let's say the radius is now here. Question?
So in that case, if you told us you wanted a percent overshoot or 20% or more, would the answer be to kind of just do this?
Yes, so the question was for that red disk and let's say that black heart logarithmic spiral corresponds to 20%. And the question was, if I now want 20% or greater percent overshoot and that settling time, those are inconsistent requirements. You would have to go back and ask, which do you want? Do you want more oscillation or do you want a faster settling time? Or can I make my settling time smaller? Can I expand my circle, my disk? If you are, so now what I should have done is made the circle a little bit more interesting, maybe to give more, how do I want to do this? Let's say that my circle, that's a circle centered at the origin. humor me. But now I have some different combinations, don't I? I might have a peak time of 1/2 or slower. Then where am I going to want to be? And I want to be inside the settling time spec. Or I want a settling time of less than what that settling time spec gives me. Where do I belong? Can you shade the region? If you want a peak time more than what that line, whoops. Oh, never do that again. I now need to be in here, don't I? Do you see how I could have you shade all sorts of different regions? Bring your colored pencils. I might have you shade, or maybe your Crayola crayons. Did you, at the beginning of the school year, did you buy your 64 count crayons? I might have 64 different regions that you need to shade. So extravagant red might be a certain place. The blue banana, is that a shade in the new crayons? Probably not, huh? Don't think I'd want to eat that banana. All right, let's move on. Is everybody comfortable with this? So now you're given transient specs, and you need to translate those into regions in the z-plane. The third category or potential question, and I could give you all three, is given a z sub delta, now find the percent overshoot, the peak time, and the settling time. Is that okay? So I can have you go 3 different ways, 3 different directions. So you need to be flexible on Wednesday, because you may get pulled in 3 different directions just for this first topic. Could give you a transient behavior and say, give me the system. I could give you the transient performance, and you could then tell me what z delta is. Or I could give you z delta. I might give you a transfer function, or I might give you a block diagram and say, what's the settling time of this system? And you're going, an all delay block diagram, I don't know how that works. And you'll ask, what are you asking? And I'll say, I can't answer that question. You'll have to figure it out. You know the material. So you now find your transfer function from this all delay block diagram. That was exam 1, wasn't it? Once you have the transfer function, you can now find the poles. Once you know the poles, that's z delta. You can find time to peak, percent overshoot, and settling time from R and theta sub D. All right. Yes. The question was, how many points am I going to deduct if your zeta curves are not very clear? No. That wasn't the question, but that was my paraphrased version of the question. Try your best. So you should know, what's the unit circle's zeta value? There's no damping on the unit circle, is there? So that zeta value is 0. Where's zeta equal to 1? A zeta value of 1 lives between 0 and 1, doesn't it? That's zeta equal to 1. It's real. And you have all your other curves in between. But you could pick a zeta, and then you could find different R's and theta D's for that zeta. And you could, in 5 points, put 5 points in your curve, and now you can connect those 5 points, and you have a pretty accurate location for that zeta. I don't think you need to get that precise. I might even give you a grid, a Z grid. MATLAB will give it to you if you just say Z grid. But you'll want to make sure your axis is equal, your horizontal and vertical are the same so that your angles are true and your logarithmic spirals are nice. Questions on that? That's the first topic area. Whoops. Oh well. Second one is Ragazzini. The direct method of Ragazzini. And what do you have there? Do you remember sort of just the two generic steps? There might be multiple parts to some of those steps, but what were the two steps? First, you need a desired transfer function, don't you? A desired closed-loop transfer function, a T sub C of Z. And that's now available to you from the first topic area. You need T sub C of Z. And that might actually impose restrictions. Your controller needs to be causal. T sub C of Z needs to have the same pole zero excess or more as your plant. That's the first restriction. The second restriction concerns zeros of your plant. Unstable zeros in your plant need to be preserved in T sub C of Z. T sub C of Z has to contain those same zeros. Why is that restriction? Do you remember? You do not want your controller canceling poles or zeros that are unstable. And that restriction allows that to not happen. Your controller will not try to cancel that unstable zero if you include that unstable zero factor in T sub C of Z. That means your original plant is retaining that in your desired closed loop system. So your controller is not going to cancel that unstable zero factor. That's the purpose for restriction 2. Restriction 3. So now I'm down to this line. It should be clear. 1 was causality, wasn't it? Pole zero excess of G sub C and T sub C are the same. This is the unstable zeros of G of Z need to be retained in T sub C of Z. The third restriction, unstable poles in your plant impose what on T sub C? Indirectly, you're looking at 1 minus T sub C of Z needs to evaluate to 0 at those unstable poles. That's restriction 3. And that's to make sure your controller does not try to cancel unstable poles, and unstable is outside the unit circle. You can have controllers that have unstable zeros and unstable poles. They just can't be canceling anything. You may have to design an unstable controller with an unstable system to get a stable closed loop system. That's where 2 wrongs might make a right. Although unstable is not wrong, but it's usually not what we want. But if you have it, sometimes you may have to, basically 2 negatives might make a positive. You just don't want to be canceling original poles that are outside or original zeros. You may have to put poles and zeros of your controller out there. They just better not be on top of pre-existing poles and zeros. And these restrictions, restriction 2 and restriction 3, make sure that doesn't happen. What's restriction 4? Do you remember? Steady state error, steady state accuracy. And that one can be kind of involved. But we probably will be most worried about accuracy due to a constant input. Okay, and that has some limiting characteristics on your T sub C of Z. What's happening to that T sub C of Z as Z goes to 1, for example? That's the first piece of Ragazzini. The second piece is what? What did we call our controller? If we call our controller D of Z, then we solved for D of Z to guarantee the right T sub C of Z that we wanted. And that was just our design formula, 1 over G of Z times T sub C of Z over 1 minus T sub C of Z. So once you've spent all this energy in step 1, finding the T sub C of Z, the second step is just turn the crank. Put it into this formula, this expression, and calculate the controller, the results. What if I gave you suppose I gave you a G of Z of Z minus 1/2 Z minus 1. And I said, I want a deadbeat response. And that's all the requirements that you have. I say, I want your closed loop system to have a deadbeat response. Any of those restrictions in play? Causality. You have to ensure causality, don't you? Which means, what does T sub C of Z have to have structurally? What kind of relationship? A pole zero excess of 1. It could have 3 poles and 2 zeros, and it would satisfy that, wouldn't it? If you had a lot of steady state accuracy specs, you might have to really crank up the number of poles and zeros. But as long as you have, let's say, 4 poles and 3 zeros, or 4 poles and 2 zeros, or 4 poles and 1 zero, you're meeting that causality, aren't you? You just can't have a constant for T sub C of Z. That would not have a pole zero excess. That would have a pole zero excess of 0, which is not satisfying your causality condition. And you know that however many poles you have, if I'm supposed to be getting a deadbeat response, does that tell you where those closed loop poles are located? That might be the first thing to try, right? What's the pole zero excess of that? 1. What was your G of Z's pole zero excess? Hey, we're getting somewhere. That's what you want, isn't it? Now, restriction 2 in play? No, we don't have any unstable zeros, do we, in our original system? How about restriction 3? Here we don't consider z equal to 1 unstable. That's okay. We're going to force it to be, our closed loop, we're going to force it to be right at the origin. So we don't have to worry about preserving that pole at z equal 1. We're going to move it in. Restriction 4. We didn't have a settling time or any accuracy spec, did we? But what's the DC gain of T sub C of Z? 1. Is that good? A DC gain of 1 means what? If I apply a constant, if I put in 4, what am I going to see out? 4. If I put in 6.28, 2 pi. Sorry. What am I going to get out? 2 pi. That won't happen in my house. If you put 2 pi in the house, you're not going to get 2 pi out the house. Probably 2 pi are going to be somewhere else, close to my zeta value. Okay? Any questions? What if we found our controller? If this is our T sub C, in our controller, D of Z, that's 1 over G of Z, T sub C over 1 minus T sub C. We're going to need T sub C over 1 minus T sub C, and sometimes it's easier to just do that sort of on the side. So that T sub C over 1 minus T sub C boils down to just 1 over Z minus 1. And when I need that up here, now I can say, oh, my D of Z, my controller, to realize a deadbeat response in the closed loop system is going to be 1 over whatever my G of Z was. That's my G of Z, times TC over 1 minus TC, which is that. That cancels, and I'm left with my controller being that. Which means that if I now apply that here to my plant, which was Z minus 1/2, Z over Z minus 1, is that what it was? Is that going to give me what I want? What I want is the transfer function between R and Y, which I didn't label, closed loop, to be 1 over Z. I'm going to cancel a stable 0. I'm going to cancel a stable pole. And I'm going to end up with, in the forward path, that. And now my closed loop system between R and Y is just that forward branch over 1 plus that forward branch. 1 over Z minus 1 over 1 plus 1 over Z minus 1. That's what I wanted, wasn't it? So it worked. That controller, and that controller was fine, gave me what I wanted. That's the design by Ragazzini. And you could make this much more interesting. I could have you doing something other than a deadbeat response. I could say, I want your poles to produce a certain settling time, a certain peak time. That's going to give you an R and a theta sub D. You can now find where those poles are. You might have to integrate or incorporate some of those restrictions. Are there questions on Ragazzini? Yes. So now what if I did that, what I'm saying in the closed loop is I want my output to be equal to my input with one sample period delay. That's my closed loop behavior, correct? So the question was, what do I do with my actuators? We've glossed completely over that, haven't we? We haven't worried about anything very physical in this design. So I had a G of Z that then was incorporating all of my system dynamics. That should have included my actuators, my sensors, etc. Now I just have a processor, a controller that I need to realize digitally, and I would like to think that you now know how to build a difference equation that would realize this D of Z. D of Z is just the relationship between the error and the input to the system. And you now have a difference equation relationship between your error and the input to the system. That's all you can really do from what you're given in this problem. Questions? Other questions? Is it clear how you would build the difference equation? If somebody from some other school, maybe up the road, said, I don't know what's going on, I can just give you a D of Z, you can go, that's fine, I'll work with this, I'll be able to implement this controller. You're okay, relax. We're good. Now you have D of Z is just that, isn't it? And it was Z over Z minus 1/2. Is that what it was? And if you factored out a Z from that, let's say I factored out a Z from top and bottom, and now if I cross multiply, I now have U of n is equal to 1/2 U of n minus 1 plus E of n minus 1. Did I do that right? That's your difference equation. That's what you would have to process. You would have to store your previous input signal. When you need it the next time, you scale it by 1/2, you add it to the present error, and put that into the system. That's driving your system. That's what this controller does for us. That's the realization, that's the difference equation of your controller. All right, third topic area is the root locus. And you should be able to just go home and play with this. You might say, give me a root locus, any root locus. And somebody might say, okay, there, start with that. Can you sketch the root locus? This should just be like falling off of a chair. It's actually easier than that, and please don't fall off of a chair. This root locus is right there. What's the red line give you? What's the root locus telling you? All the possible closed-loop pole locations as you crank up the gain K in a closed-loop configuration where your original system had a pole at wherever this was located. Maybe that's at 3/4. Is this stable capable of remaining stable for all values of gain K? Will this system remain stable no matter what the K value? Can you tell me the K value that will induce an unstable response? Might have to give you a little bit more information. Not only will I have to tell you where this pole is, but also maybe the numerator coefficient in the transfer function. And then you can look at the gain that would get you to that point right there. The gain to get you to that point is the biggest gain you better put into your system. That's assuming that this X is inside the unit circle to begin with. It might be starting outside the unit circle. Then you have a lower limit. If this is now 1 right here, then you need to know what's the gain to get me to the triangle. That's my minimum K. The gain to get you to the square is the maximum gain for stability. Is that clear? All of that from that picture. What about another picture? Like I said, you can just play with this. This is fun. All right, don't answer that. But here's another pole zero diagram. Again, you have to worry about the relative locations if you're asking anything specific, but if you're not, you know what root locus, where the root locus is on any of those 3 real axis segments. How many root locus branches are there? Is there a breakaway point? How many infinite zeros do you have? Where are your asymptotes? Where are your angles of departure? What are the angles of departure? They don't exist the way we define them, do they? We don't have any complex poles. All right. You could just sort of reverse that picture. What's going to happen there? How many root locus branches do we have? What's our pole zero excess? How many zeros at infinity do we have? Where are our asymptotes? What are the angles of the asymptotes? How many asymptotes do I have? How many infinite zeros do I have? 2. That's how many asymptotes I better have. Because my asymptotes are telling me, they're guiding me where to my infinite zeros are going, or where I'm going to those infinite zeros. Here, if I just had 2 poles, nothing else, my root locus is going to split those in half. I'm going to come together, they're going to meet right in the middle, and they're going to break away. If you have other poles and zeros anywhere, that half thing is out the window. Is that clear? What if I said, can you tell me the gain to get me to that triangle? What's the gain to get me to that triangle? Do you need any more information? What additional information do you need? You might need to know where these poles are actually located. Let's say they're at 1 1/2. Is that enough information? You need to know something about the gain in your system, don't you? What's in the numerator? You now know the poles factors. You don't have any zeros, finite zeros, but you would have to know the scaling amount, wherever that was located. You might have a number in the denominator. I might give you the DC gain. You wouldn't have a DC gain. It would be infinite if that was at 1. So I might have to give you something else. Right? I might have to say the gain at 3/4, at z equal 3/4 is this for g of z. Is that clear? What else do we have? And those just involved pretty basic pole and zero patterns. What if I give you this? What's the root locus look like? First, can you tell me which real axis segments belong to the root locus? And if I label them from right to left, I have 1, 2, 3, 4 different real axis segments. Is the first one to the right of that rightmost pole, is that on the root locus? No, because the angle contributed by all of the poles and zeros is 0, not minus 180. That segment is on the root locus, isn't it? Because any point in there, this pole gives me 180, this pole gives me 0, this 0 gives me 0. 0 minus 180 gives me minus 180. Any point in there is on the root locus. What about between the leftmost pole and the 0? It's not, is it? To the left of the 0. How many root locus branches do I have? Where do they begin? On the poles. So I have 2 branches that are approaching each other. Do they meet in the middle? They meet between them, not necessarily exactly in the middle, because you have a 0. So you have to find the relative, what? Max or min? Now you're looking for a relative maximum between, let me just put some points here. Let's say this is 1 and this is 2. Is your system stable? Open loop. I maybe don't like the way I've grouped those relative to each other, but so I will change them a little bit since I labeled that one so close. The relative picture looks the same, doesn't it? Is there any hope of stabilizing this? Kind of slim, but there might be. Depends on, I don't think it's going to happen. Is it? Why do I think that? Where's the breakaway? It's between 1 and 2, isn't it? The breakaway. It's 1.1, and this guy is to the left of 0. The radius is now 1.2. And this is at 1.1. It's never going to intersect simultaneously. Both branches are not going to be inside the unit circle, are they? So we're going to have to do more than just a constant gain to stabilize this system, but we're not worried about that yet. That's after exam 3. We worry about getting our, getting back to the food analogy, we have a 0 shaker and a pole shaker, and we sprinkle poles and zeros on the Z-plane in the appropriate location to control the system. We'll learn that later. But for now, this one maybe doesn't work unless, for whatever reason, those were at different locations. Now we're in a better position, aren't we? Now we're probably going to be having stable locations. Is that clear? What else could I present you with? What's the pole zero excess? 1. Where's my asymptote? 180 divided by pole zero excess. Where's my asymptote? 180. It's that sort of easy one or trivial one. Hopefully that leftmost pole is inside the unit circle if you're trying to stabilize this with a constant gain controller. Wake me up if I'm not doing this right. What about this one? An hour ago we talked about this system. Maybe. Yes, no. We running out of juice? Three more hours. And then you can move outside the unit circle. You can escape. No, I won't hold you here that long. But what's this look like? Can you at least shade the real line segments that belong to the root locus? So let's put some numbers to this. Let's say this is 1. Let's say this is 1. Oh, I'll make them easy. And let's say this is minus 1. They may not look very accurate, but is that okay? Now what do I do? Am I done? How many root locus branches do I have? What did I hear? In unison, 3, right? If I have 3, how many asymptotes do I? Well, if I have 3 branches, what are my infinite? How many infinite zeros do I have? What's my pole zero excess? 3, which doesn't have to always equal the branches, does it? But now I have 3 branches that are starting in the finite z-plane, and all 3 are going to go off to zeros. Infinite zeros. Where are those infinite zeros located? In what angular directions? Do you remember? Which rule is this? What's your fundamental angle? What's your base angle of your asymptote? What's the smallest asymptote angle? 180 divided by your pole zero excess, 60 degrees. That sets your rest of your locations. So it's 60, 180, and 300. They're separated by 120 degrees. All right, now I know this 3 asymptote configuration, but now I have to pin it on the donkey, don't I? I have to pin it on the real line. I don't want to be blindfolded. I know where to pin it, don't I? Where do I pin it? At the centroid, sigma sub A. Where is that? I sum my poles. I have a pole at 1, I have a pole at 1/2, and I have another pole at minus 1/2. I subtract my zeros, which I do not have, and I divide by my pole 0 excess. My centroid is at 1/3. So now I come to 1/3, which is what I'm saying is right there, and I draw a line at 60. I draw another asymptote at 300, and I don't have to draw my line at 180. And now, does that help me sketch my root locus? Without even computing the breakaway, you could just guess that to be somewhere between 1/2 and 1 if you didn't need to tell me exactly, couldn't you? I know that makes you feel nervous, but if I said, where's the breakaway, you could find it, couldn't you? It's the relative max between 1/2 and 1. So these two are moving towards each other. They break away. One branch goes to that asymptote, one goes to that asymptote, and this one goes to the third asymptote at 180. That's your root locus. Is there any chance of that being stable? For a constant gain? Pardon? Pretty good one? If I gave you, well, what are 2 gain values that you would like to have in your possession to tell me more information? If I gave you 2 points to identify on that plot, on that root locus, and I said, okay, I'm going to give you a triangle and I'm going to give you a square. You can locate those in 2 places, and I want you to use that to tell me something more about stability or a range of K for stability. To be consistent with what I've been placing, I'd put a square there at -1. Where would I put a triangle? Just to give me an idea. Here maybe there's not a correct answer, but I'm saying I'm giving you 1 point. If you were doing this number crunching, I would probably say, give me this guy, and I'll compare that K value to the K value here. It's not hard to calculate the gain at -1, is it? With complex numbers, which is what was being suggested, if you looked at the unit circle, which now I'm really nervous to sketch that. Ugh. That's a dog's hind leg. If we had a bone before, that's now the dog's hind leg. It's crooked as a dog's hind. You could find that intersection of the unit circle and the root locus and say, okay, let me compare that to the the square. But now let's say the triangle gain is 2, and let's say the square gain is 1. Okay, the insight is before you even meet at that triangle, your one on the negative left half plane is going unstable. So you can't crank up your gain more than 1. Does that make sense? So you would say k equals 0 to 1 would be your range of stability. What if it just now was actually reversed? What if the triangle was 1 and the square was 2? Do you know definitively what your range of stability on k is? Yes or no? K is 1 at the triangle and 2 at the square. It can't be greater than 2, but it probably is even going to be less than 2, isn't it? Because when you hit a gain k of 2 at the square, you may already have zipped out. Those complex roots or branches may have already escaped the unit circle. Is that clear? And you don't know from that limited piece of information. You would have to compute the values for the gain, let's say, to get you there. Let's say that was 1.5, and the square was 2. Now do you have a range for k for stability? The cloud is a gain of 1.5. The square is 2. Let's say the triangle is 1. What's your range of k for stability? 0 to 1.5, isn't it? That's assuming that that's a very accurate intersection point of the cloud. But you could then say, oh, k of 1.5, you could plug that into your closed loop characteristic equation, evaluate the roots at k equal to 1.5, check their magnitudes, and if they are 1 or less, that's still okay, isn't it, for k? Questions? So if I say put a circle around the break, so I could give you all sorts of questions for root locus. I might say something like this. I don't even know what I've sketched. Do you know what real axis segments are on the root locus? Let me see if I can put these in. Is that okay? How many root locus branches do I have? 4. What's my pole zero excess? How many infinite zeros do I have? What's that mean? You have 2 asymptotes. What are the angles on those asymptotes? 180 divided by, I maybe didn't hear right, 2, the pole zero excess. So the asymptotes are at 90 degrees, aren't they? The main one. The other one's at 270 or minus 90. Where was I going with this? Can you circle the real line segment where a breakaway occurs? Can you box the region where a reentry occurs? Is there a reentry? Depending on all these values, let's say that your centroid ends up being there. Then these are going to do this. And the relative maximum will determine where they break away. You may have no hope of stabilizing that system without some additional poles and zeros or a more elaborate controller. It depends on where all of those are located. But I could ask you for a range of K for stability. Let's say this is -1, and let's say this is 3/4. Any ideas of stabilizing this system? Will it be stable for all values of non-negative K? No, because those infinite zeros are going to exceed or go outside the unit circle, aren't they, at some point? And it's going to depend on where that centroid is and where they sort of bend around. K equals 0, is that stable? It rings, but it's stable, isn't it? Because if I ask you, okay, let's say that I now tell you that for a gain of 0.2, those are your closed loop poles. Does that make sense? As you crank up the gain K, that was 0.2, now maybe you go to 0.4. Oh, let's go to 0.8, and maybe you go there, 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 and there. Is that clear how you're moving along your root locus as you crank up the gain K? And there is a limit to how far you can crank up K before that box goes outside the unit circle. And you could get a pretty good estimate of that if you know where that centroid is. Because you know the radial distance is 1, and you might know the real part, so now you can use your trigonometry. You know the hypotenuse, you know the horizontal, you could find the y. Now you know x and y. If you wanted to, you could plug that value in for x plus jy into your K expression, and that's your gain for stability. That makes sense? Are we done? I stuck a fork in it. Was it clear liquid that came out? I think we're okay. If you have questions, I have office hours Tuesday and Thursday. Thursday might be a little late for exam 3. Exam 3 is Wednesday, but I do have office hours scheduled from 12:30 to 2:30 on Wednesday. Good luck, and hopefully everything should be available for you.